A red car stopped at a red light. As the light turns green, a blue car passes by traveling at 62 kilometers an hour. The red car takes 2 seconds after the light turns green to accelerate forward at 2 meters per second. When and how far down the road will the cars meet again? Sketch distance versus time motion for each car on the same graph. And what is the average velocity of the red car for this time of travel for the blue car, and compare both and explain the results. So for a question like this where we have two motions in objects, we have two objects in a kinematic question, we have the red car and we have the blue car. So let's take all the information we have from both cars and put it on a table. The blue car, we know its initial velocity, we call that VI, is 62 kilometers per hour. Because we know our acceleration was given in meters per second, we're going to convert this to meters per second. So that's going to be 62,000 meters over 60 minutes times 60 to give you meters per second. And that would be 17.22 meters per second. The acceleration, because it has a constant speed of 62 kilometers an hour, it's not accelerating, so the speed isn't changing. The acceleration is 0 meters per second squared, or meters per second, however you would say it. And we're trying to find its distance, its average distance, and its average time traveled. And for the red car, we know its initial speed, because it started from rest, is 0 meters per second. Its final speed we don't know because it continues to accelerate. Its acceleration we know is 2 meters per second. And we're also trying to find average distance and time. So for a question like this, we would have to refer to our 5 equations of motion. Let me grab a picture of that here. So as I said in this question, we're going to be using our equations of motion. And the one way to know which equation of motion you want to use is looking at what variable you have and what variable you're looking for. So we know we're looking for distance in both of them and time in both of them. So we're looking for an equation that has both distance and time and has all the variables we have. So if you look at both equation 3 and 4, equation 3 states the change in average distance is equal to the initial velocity times the change in time plus 1/2 times the acceleration times time squared. And equation 5 is minus 1/2 acceleration times time squared. So we know equation 3 because equation 5 uses final velocity and equation 3 uses initial velocity. We're going to go with equation 3. I'm not going to write all the equations of motion, I'm just going to write the ones we use. So equation 3 states the change, delta stands for change, and this is the vector quantity. Any questions regarding any of my signs or anything I'm doing here, you can always send me a text, Spencer, we could talk about this later. But the change, as I was saying, change in average distance is equals to, this is equation 3. Initial velocity is a vector, times delta t, plus 1/2 times the acceleration, times change in time squared. Acceleration is also a vector. So now we're going to write for this equation, we're going to write this equation for both cars. So we're going to use this equation 3 on the red car, and we're also going to use equation 3 on the blue car. Now there's multiple ways to solve this question. how I recommend solving it, the way you probably go over this in class is going up to the equations first. But one way I always recommend solving questions like this is doing a visual representation. So this is what I mean. You're supposed to draw a graph at the end, but with the information you have, you can actually sketch a graph in the start. You know the blue car, the acceleration is 0. So when your acceleration is 0, your distance, this is going to be our distance time plots here. On this axis we have distance, and on this axis we have time. So the blue car, we know it has constant acceleration of 0. So we know its distant time graph is going to be a straight linear expression. And for the red car, initially, let me move this up so it goes through 0 points, yes. And for the red car, initially, for the initial 2 seconds, like the question says, the car doesn't move. So this is our 2-second limits, 2-second point. And then it gradually accelerates, and it's going to accelerate until the point it becomes faster than the blue car and it starts to travel a greater distance. So the point where they meet is right here. At this point, the 2 cars meet. And this point is very important because this is a point you're trying to find the distance and the time. And what you notice here is from this and this, at this point, your distance and your time for both cars is going to be equal. That means if we let distance for the red car be delta dr and distance for the blue car be delta db, I'll just put this distance blue car, and this is distance red car, and we let the time for the red car be CR and the time for the blue car be TB. And we know at this point, like I said, the distance is the same and time is the same for both the red car and the blue car. We can also write this. We can say therefore delta dr at that point is going to be equals to delta dB, and delta tr is going to be equals to delta tb. So now we substitute equation 3. Let's say this is equation 2. We substitute, let's say this is our equation 1. So now we're going to substitute our equation 3 of motion into this. So remember our equation 3 stated delta d is equal to initial velocity change in delta. So now this is our equation 1. Delta d for the red car is equals to delta d for the blue car. And now we're going to write a delta d for the red car and a delta d for the blue car from our third equation of motion. And that is going to look like this. I'm going to color code it so it's easier to read and understand. So delta d was equals to, from this, for the red car we have the initial velocity of the red car, this times the change in CR of the red car, plus 1/2 acceleration of the red car is delta t of the red car squared. And this is equals to initial velocity of the blue car delta t blue squared. Now we know, remember, TR is equal to TB, and sorry, I'm gonna just make that a lot neater because we're talking about change in time. So we know delta TR is equal to delta TB, just as the distances are equal to each other, because we're talking about this specific point where the cars meet. We can equate both of them to just delta t. And if we do that and we plug in the values for initial velocity from our table here, initial velocity for both cars, acceleration for both cars, we're gonna have this as a final equation. Because the initial velocity here is 0, this all turns to 0, so we have 0 plus 1 over 2. Its acceleration we know is 2 meters per second, so we write 2 meters per second squared. We're looking for change in time, so delta t squared. And this is equals to the same thing, the initial acceleration, initial velocity we know is 17, we calculate it to be 17.22 meters per second times delta t. And because its acceleration is 0, this whole quantity changes to 0, so we have 0. And now we can solve this to find delta t. So this 2 cancels out this 2, and that gives us 1 here, so we have delta t squared. I can just put the 1 in brackets. Sorry about that, I just had to change my pen. So now we're going to have delta t squared and put the 1 in brackets. So this 1 comes from 2, canceling 2 here, and we have our meters squared, meters per second squared. So now we have delta t squared is equal to 17.22 meters per second. And we have our meters, let's not forget that. So that's going to come out useful. And this is still multiplied by delta t. And we're not going to add the plus 0. So now if we divide both sides by delta t, and we also divide both sides by meters per second, we end up with this. Meters per second squared delta t squared is equal to 17.22 all over delta t meters per second. And what happens here? This cancels out the squared, meters per second cancels out this, and you're left with second. And you're left with delta t 1 over s is equal to 17.22. And you cross multiply, you're going to end up with delta t is equal to 17.22 seconds. And this is your average time it will take both cars to meet. Now, you noticed I took the meters per second like it was a variable and I multiplied it through. This is just something I'm showing you. It will take you through solving different equations, but it helps you always remember your final units. So if you're solving for when you start to do dynamics and you start to do forces, like if you don't remember your final forces in newtons, you might be able to remember kilograms, meters squared, something, and you're going to get your full marks for that. So it's just a way to always, or you might remember that kilogram, meter squared, whatever is the actual units. So it's just a way to always get your final units correctly. You can actually just multiply your units through or divide them through your equations. As long as you actually divide them through, you follow, when you divide the variable, you divide the units. If not, you could make a mistake, and it's always good to carry it through. So here we get our average time it takes both cars to meet. We know delta t. We know delta t r is equals to delta t b, and this is equals to delta t. This is from this. Therefore, the red car and the blue car meet each other after 17.22 seconds. Both. Now, to calculate the distance, we know if the cars meet, and we're calculating the distance from the average distance from the traffic lights, they both should have traveled the same average distance. So for a question like this, we actually have a way to check our answer, because we have two formulas we can use. We can either use the formula for the red car, or we can use the formula for the blue car. So we're going to go back to equation 3. Equation 3 is a state change in distance is equals to initial velocity times acceleration times change in time plus 1/2 acceleration times change in time squared. So if we use this equation for both the red car and the blue car, to make sure our answer is correct, we should get the same answer in both of them. For the red car, we're going to have change in distance is equals to the red car acceleration. The red car, the initial velocity is 0, not acceleration. We know delta t is now 7.22. This is plus 1/2. Acceleration is 2. And I'm going to write this again with the units by the side, so you can see how all the units are going to divide up to meters. Divide and multiply up to meters. So here we have a final 0. Here we know it's going to be 0 because we have a 0 there. And I have 1/2 times 2 meters per second squared. And the change in time squared. So we know we have time squared, so this is going to be s squared. So this case is actually very simple. You can see the s squared here because this is m divided by s, and s squared here cancel each other, and you're left with m. And the final value is in meters, so that gives you your units. M is meters. So if you do the math here, like I just did on my calculator, you end up with approximately 296 meters. So basically you have 2 cancels out and you're left with 17.22 squared. Now for the blue car, we have its average distance. I'm going to use the lighter blue, it's easy to see. Have its average distance is equals to 17.22, which should be its initial velocity. We calculated 17.22 meters per second times 17.22, its change in time, plus 1/2. The acceleration is 0, so we know this whole variable is 0. And here again we have 17.22 times 17.22, and this will give us the same thing as 17.22 squared, so 96 meters. So we know our answer is correct. So what else does the question ask for? Did we cover everything? The red car stopped at red lights. Okay, when and how far down the road will the cars meet? We covered that. Sketch the d versus t motion. We covered that. What is the average velocity of the red car for this time interval? We're going to solve that. For the blue car, compare the two results and explain. So finally, for the average velocities of both cars, we know our average velocity. So as we know, our average velocity will be equals to the average distance traveled divided by our average time. So we know our average distance traveled is 296 meters, and our average time is 17.22 seconds. So this gives us about 17.2 meters per second. And this would be for both the red car and the blue car. And this is because they traveled the same distance in the same time. And also another note to add, we also know the blue car was at a constant speed of 62 kilometers an hour, which is equal to 17.22 meters per second. And if it was at a constant speed, it means its average velocity. So therefore its average velocity should also be equals 17.22 meters per second. And our plot of distance versus time is this.